Welcome back, everybody. We are in Chapter 6 now. So we have been looking throughout Chapter 5 at how to compute an integral by pretty much using rectangular approximations, by looking at them in terms of area. We've looked at some applications of those, but we haven't really figured out yet how to compute these integrals exactly and how to do it in a much more simple way. And this is where Chapter 6 is really going to help us out. So the main concept behind Chapter 6 and behind this integration is going to be the concept of the antiderivative. So the antiderivative is basically just what it sounds like. It is the opposite of a derivative, so it is undoing a derivative, so to speak. We're going to get lots of practice with these throughout the chapter. We're going to see how we can use this and apply it as well. So start us off here. So 6.1, analyzing antiderivatives graphically and numerically. So we say if the derivative of big F of x is little f of x, i.e. big F prime equals little f, then big F of x is what we call an antiderivative of little f of x. Okay. So, for example, since the derivative of x squared is 2x, the antiderivative of 2x is x squared. Okay, so we're basically going backwards now. Okay, this is why it is important to make sure that you're solid on your derivatives, because if you want to compute an antiderivative, you first need to know what its corresponding derivative is. Okay, so again, we're going to use this x squared example a lot, but since the derivative of x squared is 2x, the antiderivative of 2x is x squared. Okay, so we're starting with the derivative, and now we're working our way backwards. Okay, we're trying to find out, okay, if I have this function, what function must I have started with, right, if I took a derivative? Okay, so suppose f is an suppose big F is an antiderivative of little f. If little f is greater than 0 on an interval, so again, think about it this way. So the derivative of big F is little f. So if little f is greater than 0, that means the derivative is greater than 0. So big F must be increasing on this interval. Okay. Similarly, if little f is less than 0, okay, then remember that little f is the derivative of big F. So that means big F must be decreasing. And if little f equals 0, so the derivative is 0, okay, then that means on an interval, then that means that big F, our original here, our antiderivative, is constant on whatever that interval may be. Okay, so again, it's just all about shifting our perspective, looking at it kind of backwards from what we were used to looking at. Okay, so let's look at an example with this. So given the graph of the derivative little f prime, okay, of a function f of x and some areas, if f of 0 equals 10, sketch a graph of the function f of x, give the coordinates of the local maxima and minima. Okay, so what we have here, so typically, right, if we go back to chapters like 2, 3, 4, we were looking at an original graph and then plotting its slopes to get the derivative. Well, now we're going backwards because this function is the derivative function, and we're trying to figure out what the original looks like. Okay, so what we need to do is set up a way to figure out some of these points. So one thing we can just do right off the bat here, we know f of 0 equals 10. So there's one point that I can plot just right now. So go on our graph here, f of 0 equals 10, right there. So that's one point down. Okay, now what we need to do in order to solve this, let's look at the behavior of the graph. So again, this graph is the derivative. So that means if this area is above the x-axis, that means that the slope of the original is positive, right? And similarly, this means the slope of the original is negative, slope of the original is positive. So this tells us that, f is, let me just type this, that'll be a little easier. So this tells us f is increasing on the interval from 0 to 2, right? That's where it's above the x-axis, and from 5 to 6. That's also where it's above the x-axis, its slope. Okay, so that's from 0 to 2, and the interval from 5 to 6. So let me just specify. Okay, so f is increasing on those intervals, and then of course that means that where the derivative is negative, from 2 to 5, it must be decreasing. So we can say f is decreasing on the interval 2 to 5. Okay, so we know that we have some positive slopes, some negative slopes in here. So what we're going to be doing is utilizing the fundamental theorem of calculus. So if you recall, we looked at this briefly towards the end of the last chapter, chapter 5. Fundamental theorem of calculus says if I have the integral from a to b of some function f prime of x dx, right, some rate of change there, then this is going to be equal to f of b minus f of a. Okay, so this, just a side note over here, that was the fundamental theorem of calculus. And now we can go ahead and utilize this formula in addition to understanding the relationship between the integral and an area. So from the fundamental theorem, we know that, let's start with the first interval here, so from 0 to 2. So we have f of 2 minus f of 0. So by the fundamental theorem, that must be the integral from 0 to 2 of f prime of x dx. And remember that integral is just area under the curve. That's this whole area under here, which we already know is 14. Okay, so we have that is 14. So now we're going to cut out the middleman. Okay, so we're just going to say therefore f of 2 minus f of 0 equals 14. Okay, so basically taking this whole middle section here and saying, well, I don't really need that part anymore. Okay, so we know f of 2 minus f of 0 is 14. We know what f of 0 is, right? That was given to us in the problem. So we have f of 2 minus 10 equals 14. So f of 2 is 24. Alright, so this gives us one of the values that we need. Okay, so now let's look at what happens over the next interval. So let me do this different color. So we know f of 5, so this next interval, minus f of 2 equals integral from 2 to 5 of f prime of x dx. And we already know this area, right? The area from 2 to 5 is down here. The area is 20. But don't forget, because it's below the x-axis, it has to be counted negatively. So this is actually negative 20. Okay, and then at this point, we now know from the previous part, we know f of 2, right? That was what we found right there. So we know f of 2, so we have here, do this over here, f of 5 minus f of 2, which is 24, equals negative 20. Add the 24 to the other side, we get f of 5 is 4. Alright, so that gives us another point. And then for our last interval here, from 5 to 6, so we have f of 6 minus f of 5. That's the integral, right, from 5 to 6 of f prime of x dx. Sorry, we're kind of coming up close to the edge here. F of x dx. And that is, we know from this area right here, that is 12. Equals 12. So we know f of 5 already, right? As we found right here was 4. So f of 6 minus 4 equals 12. So f of 6 equals 16. Sorry, it's kind of tight on space in there. All right. So we got some points. Let's go ahead and plot them. So again, we already found f of 0 is 10. That was given to us in the problem. We now know f of 2 is 24. So it's going to be right up there. We know f of 5 is 4. So that's right there. And f of 6 is 16. That's going to be right up there. Okay. And now we just try to connect the dots as smoothly as possible, or try to make it kind of a smooth curve. Something kind of like that. Okay, roughly, let me accentuate where these points are. Right there, and right there. Okay. And then we can label the local max and local min. We can see up here the local max is going to be 2, 24. And local min down here is going to be 5, 4. Alright, and what we just created is the graph of the original function. So whereas before, what would happen is you'd be given this graph over here, and I would say, give me an estimate using the slopes to get the graph of the derivative. But now I'm giving you the derivative graph over here and saying, now give me the original. Okay, using those areas and applying that fundamental theorem of calculus. Okay. All right, and then one last thing to mention here is regarding concavity. So if big F is an antiderivative of little f, that means big F double prime is little f prime. So if little f is the derivative of big F, okay, if I take one derivative of little f, that puts me 2 derivatives ahead of big F. Okay, so again, big F, take the derivative, gets me f. Take the second derivative, gets me little f prime. So we can determine concavity of big F, of that antiderivative, using little f prime. So if we say that little f prime is positive on an interval, then little f is increasing, and big F is concave up. And if little f prime is less than 0 on an interval, then little f is increasing, and big F is concave down. Okay. And that's it for section 6.1. So just a short one to get us started off here. When we come back in a little bit with section 6.2, we're going to be looking a lot more at the calculation aspect of things, but we really are just getting started here with this chapter. So I will talk with you all